Hi there! Welcome to the second episode of the filters tutorial. Today we will talk about the passive first order RC low pass filter. It is a very simple filter to analyze and to design, and it will help set the stage for analyzing and design the other type of filters that we will talk about in this series. A large part of the video is dedicated to lab experiments to show you the effects of the filter and to take some significant measures on it. In between, we will also address the theory behind it, presenting the formulas to calculate the basic parameters of the filter in simple terms. I can assure you that after watching this full episode, you will be able to analyze and design your own filters of this kind. And if by any chance you are planning to buy some lab instruments like the ones I am using, I posted a couple of links in the video description below to help you out in the choice. They are the same instruments you'll see throughout this video, and if you click on them, you'll also help my channel at no cost to you. And now, let's begin. Let's start by taking a look at the schematic of a first-order RC passive low-pass filter. It is made of just two components, one resistor and one capacitor. The RC in the name comes in fact from the presence in the circuit of these two components. First order is because there is only one reactive component in the circuit, and passive because there are no active components like transistors or op-amps. Low pass because of all the frequencies injected in its input signal Vi, only the ones lower than the so-called cutoff frequency will go unaltered in its output signal Vo. All the others will be attenuated, and the more they are higher than the cutoff frequency, the more they will be attenuated. The cutoff frequency of such a filter is defined by the following formula. We will see later where this formula comes from. It tells us, basically, that the cutoff frequency depends on both the resistance and the capacitance of the component making the circuit. The greater the resistance and the capacitance, the lower will be the cutoff frequency. Readjusting this formula, we can derive the one that allows us to calculate the resistance of the circuit and the one that will allow us to calculate the capacitance. Both formulas are the ones used for the design of the filter. You arbitrarily define the value of either R or C, just one of the two, and then you use the appropriate formula to calculate the other value. It is that simple. In reality, however, you do not really choose arbitrarily one of the two values. In general, you make a list of all possible values that are okay to use in the circuitry that the filter is connected to, and then, for each of those values, you calculate the other one and make a small table. And then you choose the pair of R and C values from this table that works better for you. The choice may be dictated by the components you have available or by specific needs of the rest of the circuit, which we are not concerned about right now though. Maybe I will dedicate another video of the series to this particular subject, but I'll wait to see your comments before making the final decision. Let's now take a look at how this circuit works in practice. To do that, we will have to build an actual filter. I'll just make up one using two arbitrary values for R and C, and then we can take some measurements in lab, and finally we can verify those measurements with some simple calculations. So, for this test, I will use a resistor of 10 kΩ and a capacitor 1 nF, and let's see how such a filter behaves. Here is the simple circuit I mounted for this first experiment. This is the line where the resistor is located, and this is the ground line, and this is the capacitor between the output of the resistor and ground, basically on the output side. On the input side we see just the resistor. For the first experiment we will use the oscilloscope and the function generator, which is this device down here. The device is already set to provide an output of 10 kHz at 5 volts, and to show you the output itself on the oscilloscope I will connect this cable directly between the generator and the oscilloscope, in particular on its second channel. So let me activate it and select the output. Adjust it. So this is the output that comes from the function generator. Let me show them together. As you can see, by just changing this knob, I can change the frequency of the output and you will notice that the amplitude remains perfectly constant. They can go up and down. Here, right now we are at 2 kHz. 1 volts peak to peak means 1, 2, 3, 4, 5 volts, about 5 volts overall, and in fact the oscilloscope is measuring 5.32. Okay, now let's add another cable between the function generator and now the input of our circuit. So this is the ground side and this is the other side. So now the output generator is entering the sine wave that we see on the oscilloscope directly into the input of the filter. Let's now use the other channel of the oscilloscope to see the output of the filter itself. And so we only put here the ground again, and the output is connected over here. Now let's go back to the oscilloscope and let's activate the other channel so we can see both of them at the same time. You see right now they're almost superimposed. Let me shift them a little bit so you can see the difference. So the yellow now is the output of the filter, the blue is the input of the filter. Let me leave them superimposed so it will be easier to see what happens when we change the frequency. And now I'm gonna change the frequency from here. So let me reduce the frequency first. So I'm at 100 kHz right now, which you can see over here too. Both signals are about the same amplitude and they both are around 5 volts. Now let me increase it. I go to 2 kHz, 3, 4, 5. Let me change the scale here so you can see better what happened to the sine waves. You see what's going on? The output level is reducing, but just a little bit for now. But at the same time is also shifting with respect to the input, and that's because of the capacitor, which introduced a shift between the current and the voltage, and in particular the current is anticipating the voltage. So let me increase the frequency a little more. You see that keeps reducing just a little bit, but the phase shift becomes more pronounced. Now we are at 9 kHz. 10. Look at here now. Now we are at 15 kHz. The gap has been more pronounced and also the shift has been more pronounced. And look, we are now at about 45 degrees of shift between one wave and the other. This tells us that we are about around the cutoff frequency of this filter, but we will talk about this more later. Let me keep going. You can see now the output is going lower, lower and lower while the frequency is increasing. Let me increase the scale here so you can see better. So for example, right now we are at 30 kHz, while the input is still at 5 volts, the output now is just about 2 volts. Let's keep going a little bit further. Now we are about, let's go to 60 kHz here. Look at this now. The output is very low, so we have almost eliminated the signal from the output. Now it's below 2 volts, it's about 1 point something volts. And look at the shift, it's about 90 degrees now. And the output anticipates the input. So you can see this is the effect that a low pass filter does on a wave. You see now I keep increasing the frequency, but at this point there is no more change in the phase shift. However, the level of the signal keeps going down, down and down further. Let me show you what happened when I go really further down. For example, 200 kHz. See, the signal is almost gone. 300 kHz. Even lower, but the shifting has stopped, as you can see. And the signal is almost gone now. The magnitude of the signal is almost gone now. 400 kHz. 500 kHz. Look at that. The output signal is practically gone now. Let's go back down with the frequency. This is 100 kHz. Let's move to 90, 70. Let me change it here so you can see better what happens. See now, the phase shift is still the same, but the signal is increasing. And now the phase shifting starts changing too. You see, it's not anymore 90 degrees, something less than 90. You see now the shift is about 45 degrees, and here the signal is becoming higher and higher and higher and higher again. And you see the phase shifting is getting towards zero, until when we are at very low frequencies, it starts to disappear entirely. You see, if I go even further down, you should be able to see now the two signals are basically overimposed. Same magnitude and same phase. So something happens at some point at a particular frequency when things start changing abruptly, and this is what the filter is for. Let's see that in a different way now. For the next test, I'm going to disconnect the generator here. I'm going to turn this off. I need to trigger on channel 1, otherwise we won't be able to see anymore a stable image. So now that I have disconnected this, I'm gonna instead move the input of the signal, which is this cable. I'm gonna put it on this other device that some of you may recognize as the noise generator I built some time ago, and for which I made another video about it. This noise generator will be set to provide a white noise. Basically, white noise is a mix of all possible frequencies in the spectrum with about the same power. And so when we introduce this signal into the filter will basically let all the frequencies generated by this device below a certain reference frequency, which is the cutoff frequency, stay there, while all the others above the FC will start decreasing further and further, like we saw on the oscilloscope before. So let's try to do that now. But before doing this, well, let me turn this on. And here's the noise. Let me increase a little bit the sensitivity so we can look at it better. You see, this is the white noise that this generator is producing, and we are injecting it into the filter, and the output is catched by the oscilloscope, and we can see it over there. This is the white noise at the output of the filter. Let's look this from another perspective now, and let's look at it instead of in the time domain, let's look at it in the frequency domain. Basically, this image shows us how the filter behaves at the changing of frequency. You can see for low frequency we have high amplitude. Look at the top of this curve, don't bother with the bottom because the bottom is just the ambient noise, but the top of it is mostly what we want to see. So over here, this is the zero and this is the maximum in this range, which is set right now to 125 kHz. You can see the low frequencies, the signal has a higher level, and when we keep increasing the frequency, the signal goes a lower, lower, lower and lower level. A diagram like this is called a Bode diagram. Let's change the scale now, so we can try to figure out what is the cutoff frequency of this filter. As you can see, I'm reducing the range of frequency across the screen. Now I'm taking just the first 25 kHz, from 0 to 25 kHz. And each division is basically having this 5 kHz. So you see, the oscilloscope gives me a bunch of information in here. It tells me what is the range of frequencies over here, which is from here, 0, to here, which is 25 kHz. And then this other number over here tells me what is the change in frequency in just one square of the screen. So basically this says 5 kHz, which means this is 0, 5 kHz, 10, 15, 20, 25 kHz, this is the mark. And then 30, 35, 40, 45 and 50. So the whole range here is double this number, 50 kHz. And you can see that we can still see the numbers declining over here. So this is called the Bode diagram, and it tells us how the level of the signal, the magnitude of the signal changes with the change of the frequency. Let's try now to figure out what is the cutoff frequency of this filter. The cutoff frequency is defined as that frequency at which the magnitude of the signal is 3 dB below the maximum value it can have, or in other words, the power of the signal is 50% less than its maximum value. To do that, we need to have the possibility to measure this range on the video. For that, we will use the cursor option of the oscilloscope. I'm gonna set it for magnitude, which is the one we want to measure. So I'm gonna set up the first indicator. Let me put it over here right now. So vertically here we have 5 dB per square. The square is divided in 5 parts, which means each little tick over here measures 1 dB. So now I'm gonna move this other bar 3 ticks below. There we go. So we can measure exactly the 3 dB range vertically. And let me lock that in place. So now I can move this up and down and they will be locked at 3 dB. But now let me do something more than that. Let me move the signal over here horizontally so that the 0 is right here. And let me adjust the height so it will match the upper line over here. Okay, this seems about right. There we go. Now let's move this back until we hit the point with the top of this picture with the bottom of this interval. And so we'll see where the cutoff frequency is. It will be displayed exactly right in this place. See, so far we still have peaks that go above, so we move forward. We still have peaks around on this side, so we still need to move along a little bit further. There are peaks here and there still. Since all the frequencies generated by a noise generator are different frequencies and different amplitudes, it's difficult to do these measurements because the top of this line keeps jumping up and down. So we had to make a rough estimate to do that. And I'm thinking I'm gonna stop over here. Seems pretty good. I mean, here there is almost nothing else, and here there are still things. So this is basically the frequency, the cutoff frequency, which seems to be 16 kHz for the component I've chosen. So here is how you measure the cutoff frequency of a filter using an oscilloscope with capability of showing images in the domain of frequency. If you have, instead of an oscilloscope like this, you have an actual spectrum analyzer, it will work basically the same way. The other thing I want to show you how to measure is how we determine how fast the amplitude goes down with the increase of the frequency. To do that, let's bring the image over here. Let's change the scale a little bit and increase the frequency. There we go. So we can better see the descending shape. Now, when we define how fast the amplitude decreases with the increase of the frequency, we use two reference points in general. Either we go with dBs per octave, where an octave is an interval of frequency where the higher frequency is exactly double the amount of the lower frequency, or we can go in dBs per decade. So let's measure it that way. I mean, 6 dB per octave, for example, correspond exactly to 10 dB per decade. So if we measure one, we have also the other. So if you are more concerned on the actual scales of frequency, you use per decade. If you are more into filters for musical instruments and so forth, you may want to use dBs per octave instead. This time we are going to use again the cursors. We establish a level with the first cursor, and then we pick the frequency which is 10 times higher, the decade, and then we measure with the cursor what is the interval in terms of dBs. So let me put the picture in a way that it will be easier to make the measurements. So okay, so we are right here, and basically this is 24 kilohertz. Now I'm going to move to 240 kilohertz and measure it again. And it's actually about here, right? This was the beginning, this is the end, and the interval is 10 dBs. So basically, in a decade, the signal decreases of 10 dBs. So we say that this filter acts with an attenuation of 10 dBs per decade, which is the same as to say which attenuation is 6 dBs per octave. Let's see now how we can calculate the cutoff frequency based on the value of the circuit components. This is our low-pass filter. Vi is the input voltage and Vo is the output voltage. The resistor and the capacitor act as a voltage divider, where we have a resistance given by the resistor R and a reactance given by the capacitor C. The reactance is basically measured in ohms like the resistances, and it represents the resistance of a capacitor, in this case, when an alternate voltage at a specific frequency is applied to it. And the reactance is not a constant but changes with the frequency. So, because of the voltage divider, we can write that the output voltage equals to the ratio of Xc over R plus Xc multiplied by the input voltage. And because of the definition of the capacitive reactance, we can also write that Xc equals the inverse of the product 2 pi Fc. And here we can see how the reactance for a capacitor of value C changes inversely to the frequency. The ratio between the output and the input voltages can be then written this way, as Xc over R plus Xc. And then, substituting Xc with its own expression, we can end up with the final formula of 1 over 1 plus 2 pi FRC. And now, remember that we said that the cutoff frequency is defined as the frequency at which the amplitude becomes half of the maximum possible value. So we can now compare the two expressions, and since the numerators are the same, 1, we can say that also the denominators must be the same, and therefore 1 plus 2 pi FRC must be equal to 2. Resolving for f, we obtain the cutoff frequency, which is 1 over 2 pi RC. Note that the voltage ratio of 1/2 corresponds to an attenuation of -3 dB, so that's consistent with the definition we gave of cutoff frequency while we were in the lab. So, going back to the initial schematic of the low-pass filter, based on the values we assigned to the resistor and the capacitor, we can now calculate the cutoff frequency of the circuit, which is 15.9 kHz, very close to the number we measured in lab. And if we now generate the Bode diagram from the previous equation of the voltage ratio, we obtain this picture, which is represented along with the diagram of the phases. Remember what we saw in lab? When we were injecting an input signal with a very low frequency, input and output signals were perfectly in phase. But then, once the frequency grew higher, we started seeing a shift of the output signal with respect to the input, and at the cutoff frequency, the shift was 45 degrees, while at the very high frequencies it was 90 degrees. Well, this phase diagram provides the graphical representation of what we saw, and all the numbers have a negative value that represents the direction of the temporal shift introduced by the capacitor. From the Bode diagram instead, we can see the graphical representation of the cutoff frequency, that we can read on the x-axis at the point where the y-axis shows the 3 dB attenuation of the signal magnitude. Let's now go back to the lab and run 2 more experiments. In the first, we will use the same circuit we used previously. This time, however, we will input a square wave rather than a sine wave, and we will see what happens to the output in this new condition. And then we will also input into the filter what is called an impulse, which is basically a square wave but with a duty cycle very small. A square wave with the upper crest lasting for a very small fraction of the whole period of the wave. And again, we will see what the output of the filter looks like in this condition. Let's do it. For this other experiment, I reconnected the cables in such a way that the output of the function generator will go to the oscilloscope, right here, and the other end will go directly to the input of the filter that we are testing, and instead the other goes directly to the oscilloscope itself. So here is what we are seeing right now. I have generated this time a frequency of 4 kHz, but this time instead of using a sine wave, I'm using a square wave, again with the amplitude of 5 volts. This is a square wave to the input of the filter, but look what the output looks like. Basically, when you see something like this, you know that you have in front of you a low-pass filter. Basically, there are high frequency components that allow the signal to come straight up like in the input over here, but the filter is removing those high frequency components, and so the square wave at the output of the filter gets smoothed out like this and when it goes up, and like this when it goes down. We can even measure these numbers to see how fast is the filter to raise the signal from the bottom to the top and how fast it is to put it back down. And these two informations are called the rise time and fall time. We can measure them and using the cursors again, but this time we'll do it in the time domain since we are measuring time right now. The rise time is defined to be the time needed for the output of the filter to go from 10% of its maximum value to 90% of its maximum value. So to do that, let's just work on the output itself. I'm going to remove this track here so we can expand this one and we can make more accurate measurements. So let me center it first, and then I'm gonna adjust the amplitude and the frequency to see the best of it. Okay, so here let's adjust the signal so we can easily measure it. So here is our 0 and the top is 1, 2, 3, 4, 5 volts. So this is 5 volts amplitude. So we need to measure from 10% of this, so from 0.5 volts to 90% of it, which is 4.5 volts. So let's get the cursors again and let's do this kind of measurement. This time we are gonna use measure frequency, and the source is gonna be channel 1, of course. There we go. So let's start with the start cursor, of course, and so let's position it in the place where the signal has 0.5 volts. So we need to put this cursor, so we go from 0 to 0.5. This is 1, so 0.5 is half the way. So it should be about here. Right? And now let's position the other cursor at 95%. So we move it. So this is 5 volts. We want to go at 0.5, which is about here actually. This is easier. There we go. Look this. And here is the time between these 2 points, which is 23.6 microseconds. So this is the rise time for this filter, 23.6 microseconds. For this filter in particular. Let's measure the fall time now. The fall time is defined as the time needed to go from the 90% of the value down to 10%. Basically it's just the opposite as the other one. So we want to see the other end of the wave, not this one. Let me see if I can use the trigger menu to show the other end of the curve. So here, there we go. So now what we need to do is just to set up the cursors so that we go from 90% with the start cursor to 10% with the end cursor. So we are gonna set the first cursors at 90%, which now we know how to do that. It's about here, half the way, and then to 10% with the other cursor. So 10% it's about here, and so the time, the fall time is 22.40 microseconds. As you can see, for this kind of filters, rise time and fall time are about the same. So here is how to do that. The last thing I want to show you is the response to a sudden change of the signal. For that, I'm gonna change here the signal. I'm gonna use this one, which is still a square wave, but now I can adjust the duty cycle and I can basically make the wave very thin. Okay, so this is a spike. So let me go back here and show you the two things at the same time. Here. So these are now the impulses coming from the generator, the blue ones you see, and the yellow ones are the responses at these impulses. Let me put them up so you can see them on top of one another. So you see every time there is a sudden change in amplitude, there is the same sudden change on the output of the filter, but then when this goes away, it takes some time for the change to cancel, and this is because of the fall time of the filter. And that's all for the passive first order RC filter. We have seen how the filter behaves at the change of frequency of the input signal, we have both measured and calculated the cutoff frequency of such a filter, and we have seen how to design a filter that provides the exact cutoff frequency that we need. We have also seen how to take some basic measurements with the help of an oscilloscope, the cutoff frequency itself, as well as the rising and falling time of a step signal or a square wave. And finally we look quantitatively at the response of the filter to an impulse. Next time we will go through the same steps to study a passive second order RC low pass filter, and we will see how its response differs from the first order filter. Thank you for watching this video, and please give it a thumb up, which will help to improve its visibility so others can enjoy it too. And finally, don't forget to subscribe if you haven't done so already, so you can be automatically notified of new videos. A small monetary contributions will also help me in making more and better videos for your enjoyment. Details are in the description below. See you in the next video, and as usual, happy experiments!